right? So once 17 question. Okay, just we'll finish this, then we'll come to this. Okay. Right. So question number 17. Okay. So the question is, a wire is made of a material of density 10 gram per centimeter cube and breaking stress 5 into 10 power 9 Newton per meter cube. What length of a wire what length of a wire will break under its own weight when suspended vertically? When suspended vertically. So let us try to work out this here. Um, this one, 17th one, right? So what is given? Let us try to take the data first. Yes, it's given that a wire made of a material of density. Density of the material is given. You can take density as D or rho or any symbol. Okay, density equal to 10 gram per centimeter cube. Centimeter cube. Better convert into SI units. Okay, and so it is equal to 10 into gram. 1 gram equal to how many kilograms? 10 to the power minus 3 kilograms. Centimeter is equal to how many meters? 10 power minus 2. So whole cube means by 10 to the power minus 2 whole cube is 10 power minus 6. So it becomes 10 power minus 3. It comes here and it becomes 10 into 10 to the power plus 3, 10 to the power 3 kilogram per meter cube is the density in SI units. Okay, a wire made of a material of density this much, and breaking stress. Breaking stress, we will take it as force by area is stress. Let us say this breaking stress of 5 into 10 to the power 9 Newton per meter square or Pascal. What length of a wire will break? What length of a wire break under its own weight when suspended vertically? So if you have a wire suspended something like this, its weight will act downwards as mg, so it will elongate. If you have some maximum weight, the weight will be so much so that the constructions will happen in the wire. That means the wire will elongate. The wire will elongate more and more and more. Then it will break automatically because of its own weight. For what maximum length it will happen is the question. For what maximum what do you call length the breaking it will happen on its own because of its own weight is the question. So we know breaking stress. We know that breaking stress breaking stress is nothing but stress. What is the formula for stress? Stress is force by area. Force by area. So you can express the breaking stress is nothing but breaking stress, and stress is nothing but force by area. So this is equal to, so here force which is acting on this is nothing but its weight mg by area, right? Here m can be expressed as, this is equal to m can be expressed as, because density is equal to mass by volume. In this you can write mass equal density into volume, right? Mass equal to density into volume into g by what is that, area. This volume can be expressed as d into area into length of the wire gives you volume of the wire, into g by a. So a gets cancelled, you get d into L into G, density into length into G is a breaking stress. So now we can say this implies breaking stress is equal to D into L into G. The question is, if breaking stress of a wire is this much, is 5 into 10 power 9 Newton per meter square, and density is this much. For what length of the wire the wire will break on its own is the question. For what length means what is the value of this? So this implies you can say L is equal to breaking stress divided by density D into G. Breaking stress is given as 5 into 10 to the power 9 Newton per meter square SI units. Density is 10 into 10 to the power 3, that is 10 to the power 4. Density I have converted here, right? 10 into 10 power 3, that is 10 power 4 kg per meter cube. That is density into G. Let us take it as 10. Okay, based on the options, if you want you can take the other value also. Let us take 10 power 5, this 10 power 5 will cancel, means 10 to the power 4 remains, so 5 into 10 to the power 4. Is there any such option? Therefore length of the wire should be 5 into 10 to the power 4 meters. This can also be expressed sometimes if you based on the options. You have to simplify this as 10 power 3 meters is 1000 meters is 1 kilometer, right? And also write it as 50 into 10 to the power 3 meters or 50 kilometers. If you have a 50 kilometer wire with this much density, then it will break on its own. So that much length you will need to for the wire to break on its own with that particular density. Okay. Next, which question, man? 11. Any other? So 11th question. So it is given that a solid sphere hung at the lower end of a wire is suspended from a fixed point so as to give an elongation of 0.4 mm. 0.4 mm. When the first solid sphere, when the first solid sphere in the first solid sphere is replaced by another one made of same material. Same material means immediately you have to understand that Young's modulus will be same. Okay, modulus of elasticity will be same material but twice the radius. Then new elongation is what? New elongation is what? So let us try to note down the given data. 11th one. So it is given that a solid sphere hung at the lower end of a wire is suspended from a fixed point so as to give an elongation of. It is given that there is a wire, there is a support to this. The wire is a solid sphere is hung at the lower end of a wire. There is a wire. You can take like this also. Instead of two stands, only one stand at stake. There is a wire. A solid sphere is hung at the lower end. Lower end of the wire, so as to give an elongation of. Elongation if you represent with E, so it gives elongation E is equal to how much? 0.4 mm. So it is equal to 0.4 into 10 to the power minus 3 meters, or 4 into 10 to the power minus 4 meters, right? And also write it as 4 into 10 to the power minus 4 meters, right? So that what is that? When the first solid sphere is replaced by another, so the wire is same only. When the first solid sphere is replaced by another sphere made of same material but twice the radius. So twice the radius, like this. Its radius is, let us say, r1 and its radius is r2. So that r2 is equal to what? 2 times r1, twice the radius. The new elongation is what? What is the new elongation? Let us see, this is E1. What is E2 is the question. Is it clear? So that means the wire is same. The length of the wire and material of the wire is same. Area of the wire and material is same. Means Young's modulus is same. So here length, area, and Young's modulus of the wire is same. Both the wire is not changed. Only the sphere is changing. Then in terms of the radius of the sphere, then how to find the elongation? You have to understand. We know elongation is nothing but what? Elongation E is equal to F. What? F L by A into Y. Yes, because Young's modulus is equal to stress by strain, that is FL by A into E delta A into delta L. Delta L can be taken as E elongation delta L or E. So that E is nothing but FL by A into Y, right? Now here, We are applying the force is acting due to this mass or weight, this is due to the sphere. The force acts due to this. This is equal to mg, right? So L, A, Y all are same. Yes or no? Only this is because we are changing the what do you call sphere have the different radius means the force changes.
So area should change.
Area of what?
Area of sphere.
Area of sphere changes, but this area is of what? This is
Wire.
a area of the wire. It all of those remains constant. So you can say elongation is directly proportional to F only, where F is force acting. Force acting can also be expressed as E is proportional to force is nothing but what? M into G. G is constant. So here this it can also express it as E proportional to mass can be expressed as density into volume into G, right? So you can also express here because in terms of radius you want. So density and same sphere of material means density is same, G is also same, radius only is changing, that means volume changes. The E proportional to V. So you can see E proportional to only V, these are constants, where volume of a sphere is what? 4 by 3 pi r cube. Yes, 4 by 3 pi r cube means you can say because V is equal to 4 by 3 pi r cube. So these are constants. So you can say E proportional to r cube. Directly take down this. So what is this? Here you can take. Yeah, okay. Here only let us take E2 by E1. E2 by E1 is equal to R2 by R1 whole cube. So this implies E2 is equal to E1. E1 is how much initial elongation is 4 into 10 to the power minus 4. 4 into 10 to the power minus 4 into R2 by R1. What is R2? R2 is twice the definition, first one, right? 2R by R whole cube. So R cancel. 2 cube is 8. So it is 8 force 32. 32 into 10 to the power minus 4. Yes. So 10 to the power minus 4 meters. Meters. So E2 is equal to. So, but the options they are given in millimeters. So we can write it as 10 to the power minus 1 into 10 to the power minus 3 meters. That is millimeters. Or you can write it as 3.2 millimeters. This is the new elongation. Got it? This is how we are looking at it. Next,
14.
14. Yeah. So it is given that an iron wire and a copper wire having same length and cross section are suspended from same roof. Young's modulus of copper is 1/3 that of iron. Then the ratio of the weights to be added at their ends so that their ends are at the same level. Ends are at the same level means elongation should be same. That is the meaning of it. So let us try to consider this here. Question number 14. It is given that iron wire and copper wire. Let us consider here. This is iron wire. Here we have copper wire. This is iron wire. This is copper wire. Iron wire and copper wire having same length and cross section. So this length, its length and its length same, and same length and cross section also. Area is also same. Area is also same. They're suspended from the same roof. So the Young's modulus of the copper is Young's modulus of this is let us say this is y2, this is y1, right? It is given that y2 Young's modulus of copper is 1/3 of
Y1.
1/3 of y1. 1/3 of y1 and that of iron. Then the ratio of weights to be added. Ratio of weights means so here when you add some weight they will elongate so that the weight is so that that weight gives what force. Force is nothing but weight. So here let us say this is F1 or W equal to W1. This is F2 is equal to W2 because of some load. So both should one is iron, one is copper, but still even though y1 y2s are different, still both will give same elongation. But that means at the end, so that their ends are at the same level means elongation given by given in both wires are same. E1 equal to E2 equal to E, let us say. So then elongation is same. Then how to find the ratio of weights? is what is F1 double F1 by F2 or W1 by W2 is equal to what is the question, right? How to find? You know, you can take from this condition or elongation condition, any condition you can take. Y2 equal to 1 by third of y1, right? So from this one you can take, otherwise y equal to stress by strain. So stress is nothing but what? Stress is,
Force by
I can say this F by A into delta L. So y2 is F2, actually it is FL by A into delta L. Here it is E, elongation is E. So F2 L2 by A2 E2 is equal to 1 by 3 times F1 L1 by A1 E1. But L1 equal to L2, lengths are same, and A1 equal to A2, areas are same, elongation is also same, what you have understood, right? So if all this cancels out, then what is this? F2 is equal to 1 by 3 F1. So directly if you want F1 by F2, so F1 by F2 you take it here. So then F1 by F2 is equal to 3 or 3 by 1 or 3 is to 1 is the ratio of forces, or you can also call them as weights, W1 by W2. So is there any such option? 14th one, 3 is to 1 or 1 is to 3? 14, 3 is to 1. Is it clear? Right. Next.
so you finished one.
Exercise 2. These two are similar ones. Let us see. So this is question number here 15 and this 19 in exercise 2. Both are similar kind of ones. These two you can understand by just looking into this, right? So listen to this. Listen to this. So the question number 15. Level 1, exercise 1. Level 1, exercise 1. So what is given here is a steel wire, 15th, this one. A steel wire of uniform cross section 1 millimeter square is heated to 70 degrees Celsius and stretched by tying it to two ends rigidly, okay, at that temperature. Calculate the change in tension on the wire or in the wire when temperature falls from 70 degrees Celsius to 35 degrees Celsius, given that alpha of steel, that is we call it as the coefficient of temperature of steel, is 1.1 into 10 power minus 5 per degree Celsius. Young's modulus of steel is 2 into 10 power 11 Newton per meter square. What is given and what you are asked to find? So area is given, initial temperature is given, final temperature is this. When they're stretched by tying to rigid supports, we are asked to find what? Calculate the change in tension. Initial and temperature is this, tension will be some T1, and temperature is decreased to this, temperature tension will be changes to some new value. So what is the new value? So that the change in tension you have to find out, right? By making use of this. So let us try to understand how to do this, right? So it is given. Uh, change in tension you are asked to find, right? So what you have to consider here is temperature change is temperatures are given, and area is also given. So area is equal to, what is this? What is the area? 1 mm square. 1 mm square, or it is equal to 1 into 10 to the power minus 3 meter square, right? Oh, minus mm square, so minus 3 whole square, so it is minus 6, right? 10 power minus 6 meter square, right? And what else is given? Initial temperature is, I can take it as theta 1, and there is some different symbols you can take. Temperature T1 or theta 1 uni symbol you can use. And this initial temperature is theta 1 is 70 degrees Celsius, and theta 2 is 35 degrees Celsius. So that the change in temperature we need, that is equal delta theta equal to theta 1 minus theta 2. Theta 2 minus theta 1, usually the difference will take actually it is theta 1 difference theta 2 or theta 2 difference theta 1. 70 minus 35 is how much? Hmm? Equal to 35 degrees Celsius. If so, calculate the change in tension on the wire. Change in tension delta T. This is not temperature, tension. This is change in tension. Change in tension. Delta T equal to change in tension is equal to what? How to deal this is, we know stress, thermal stress. We have to deal here a concept called thermal stress. Stress is equal to force by area. Once again, yeah. You know, stress is equal to force by area. But here, so when you attach, it is given that is a wire reheated to some temperature is attached to two rigid supports like this. So a tension is developed in this. So from this tension in acting in this direction, same tension will be there. If it is light sting, massless sting, you can call it as. So same tension will be there. So initially, when it is at a temperature of 70 degrees Celsius, there will be tension T1 at theta 1. When the temperature after some time, if you leave this for some time, so that when temperature decreases to theta 2, which is equal to 35 degrees, then tension here will be reduced to some T2. So that what is, when change of temperature is this is happening, then what is the change in tension is the question. So you have to take here the tension is nothing but force. Stress is force by area, right? The force per area here, the force is nothing but tension force by area. So you can take it as T by A. Stress equal to T by A. But this stress is nothing but thermal stress. Thermal stress. This can be expressed as T by A is equal to thermal stress. Thermal stress. So it is equal to here, if you observe few more things are given in the data. I forgot to note down here. What are those? Alpha of steel is equal to 1.1 into 10 to the power minus 5 per degree Celsius, and Young's modulus of steel is equal to 2 into 10 to the power 11 Newton per meter square of Pascal. So, how to find this change in tension in terms of the alpha and Young's modulus also is the question. So, what you have to remember is Young's modulus is equal to stress by strain. Stress by strain, right? So we can call it as thermal stress by thermal strain. But stress is nothing but force by area. Here we can call it as tension by area, right? Strain is nothing but delta L by L. Okay. But in this case, delta L by L, when temperature is increased, you can take this as let us say this is from this you can write this stress is thermal stress. So you can, this implies thermal stress thermal stress is equal to y into strain, that is y into delta L by L. Y into delta L by L is thermal stress. So are you following? Let us say this is equation 1, this is equation 2. Not only this one, let us do one more step, then you can take equation 2. Are you following here? So what you have to understand here is thermal stress is equal to, this implies thermal stress is equal to y into, in thermal properties you might have studied, with increase in temperature the change in length is represented as delta L equal to delta L proportional to its original length and the change in temperature. So delta L is equal to alpha into L into delta theta. So delta L by L is alpha delta theta, where alpha is temperature coefficient, linear coefficient of temperature. unit coefficient of temperature. That is thermal stress. If you take this here, if you take this is equation 2, so from 1 and 2, this implies T by A is equal to Y alpha into at some temperature. You can take it instead of taking this temperature difference, you can take it as at a particular temperature thermal stress theta 1, right? You can take this as theta, right? So at particular value of theta, you will have T, right? Area will be constant, y will be constant, and of course, and the alpha coefficient of this thing, temperature coefficient. Then you can say that T changes, theta changes, T also changes accordingly. So from this we can say, if you take this is first condition, T1 by let's take this is thermal stress due to this. Or directly you can take by keeping this constant. If theta changes, that as thermal stress is the tension by area, you can say tension also changes. Delta T by A is equal to Y alpha into delta theta. Are you getting? By A is equal to Y alpha into delta theta. Delta theta is given, alpha is given, Y is given, area is also given. Change in tension can be obtained by using this relation into A. Right? What is this question number? 15. Hmm? So you can say it is equal to, so change in tension is equal to Y alpha delta theta into A. Into A, y alpha into here, this is alpha actually, into this is some different symbols that are given, you have to take it as into A. So all the values are given, substitute, then on simplifying we'll get approximately 15th one 77. What is the tension, right? 77 Newton. 77 Newton will get. Change in tension, T is tension, not temperature, theta is temperature here. Okay, that's it. Same way, take that. Yes. Uniform stimulation of length 1 meter, area of cross surface, ranging from fixed support. Find increase in length of the rod. Means with its own weight, with its own weight, increase in increase in length with its own weight. Uniform rod 20. Hmm? Hmm. Yes. Okay. Hmm. See level 2 exercise 1 question number 6. So load of 1 kg weight is attached to one end of a steel wire of cross-sectional area 3 millimeter square and Young's modulus 10 power 11 Newton per meter square. The other end is suspended vertically from a hook on a wall. Then the load is pulled horizontally and released. When the load passes through its lowest position, the fractional change in the length is. So I'll take it as what is that? Vertical circular motion condition. Then I'll take the centripetal force. That condition. And this I think I have given. I forgot to given one relation. Young's modulus in terms of interatomic distance. Young's modulus. Young's modulus in terms of interatomic distance is and force constant is what do you call it? Molecular force interatomic force or molecular force is equal to Young's modulus into interatomic distance r. There is a relation between those force constant and Young's modulus and r. Directly by using this, you can calculate the required parameter here. Okay, in question number 4, level 2 exercise 1. Okay, the direct relation.